Now that we've taken a look at prefixes and metric units, the next video in this series for Unit 1, we're going to take a look at significant figures. Every experimental measurement, no matter how precise, has a degree of uncertainty in it. And we use what we call significant figures to help us understand the amount of uncertainty that is in this measured amount. There's always a limit to the number of digits that you can produce in your in a measurement. Now, why does this matter? This matters because depending on how precise of an instrument you are using, when you, let's say, have to do a calculation using more than one physical measurement, your calculation cannot be more precise than than the tools that you were using to get the measurement. So anytime you see a value in a problem that has a unit next to it, 5 grams, 5 milligrams, 5 kilograms, right? Know that that was measured by an instrument. And the value that you see written is based on the precision of that instrument. Now, what do we mean by a degree of uncertainty? Let's take a look at this. Graduated cylinder. What would we put as the value for this volume? Well, if I blow this up a little bit, what can you read precisely on this graduated cylinder? There's a 15, 16, and 17 milliliter marker. But that decimal place we cannot read, right? We can guesstimate what that value would be. What do you guess it will be? My guess would be, being that we have to read the meniscus of this value, I would say that I'm not going to read this top part. I'm going to read down here. I would say that this is 17.5 milliliters. Now, notice how you and I may see this value a little bit different. Notice that last digit is the estimated or uncertain digit. So when we record the value of the volume in this graduated cylinder, we could say it's 17.5 milliliters. Maybe it's 17.6 milliliters, right? This value has 3 significant figures. It is all of the known digit plus 1 estimated digits. We know the 17. We can read it clearly on our graduated cylinder because we have 15, 16, 17, right? How do we know that this is 17? Because this large unit here is 20. And if I count 15, 16, 17, 18, 19, 20, I know that this line here represents 17. That uncertain digit would be the decimal place. So the significant figures tells you the uncertainty in the observed and calculated values, right? So these are all the meaningful digits that are used to express a value. Let's take a look at these 3 rulers. Which one of these rulers would you say is more precise? Why would you say it's more precise? Which one of these rulers do you think would give the more accurate measurement? Let's take a look. In letter A and letter B, we have the exact same piece of wood that we're measuring on 2 different rulers. Let's take the measurement of each of these objects. Looking at letter A, I would measure that this object is about 4.5 centimeters. What do you think? Let's take a look at number B. Being that this ruler has more little hashes in between, I can clearly measure 4.5, and then I'm going to guesstimate that last digit as being 4.55. What do you think? Now, let's take a look at ruler number C. What would you say the measurement of this piece of wood is? Would you say it's 3, 3.0? Would you call it something different? Well, if we're considering significant figures, remember when we're taking a measurement, the measurement has to have all of the known values plus an uncertain digit. What is the known value that we have here? Well, that known value is 3. Can we guesstimate if we were to use this ruler just like we did for A? Could we guess what that first decimal place would be? Sure we can. But being that this measurement is directly on the line, we're going to indicate that uncertain digit as a 0, 3.0. So now, again, which of these measurements is more precise? Which one do you think? Why? I would say letter B, because I'm able to measure to 2 decimal places instead of just 1. Which of these have a more accurate measurement? Well, because the precision on this ruler is a little bit better, I can get a more accurate measurement than using either the rulers in A or C. So how do you determine what significant figures are in a given value? Once again, folks, these blue links here are clickable in your presentation that you have posted on Top Hat. So, what is a significant figure? It is a measured number, and the significant figures are all the digits, including the estimated digit. So, if we go back here, how many significant figures would you say is in this value? We've got the known number, which is 4, and this uncertain digit, which is 5. How many sig figs, which we'll call it for short, do we have in this first value? Count them. 1, 2. Good job. What about for B? How many significant figures do we have? Well, we know that we were able to accurately identify 4.5, and then that final digit, which was uncertain, which would make it 3 total significant figures. So there are a couple of rules that we have to use when we are looking at measurements. And significant figures have to do with measuring the associated error. Do you remember in video 1 where we talked about mass, and when we were looking at the balance where it said 5.01 grams? Which one of those digits do you think was the uncertain digit? Do you remember that on that image, we saw that the last decimal place was a 1. If you're taking the lab, you'll see that when you put something on a balance, that last digit fluctuates until there's no air moving around or something like that. So that last digit is uncertain. What do you think was the number of significant figures that were provided by that balance from video 1? If the measured value was 5.01. Anybody know? Correct, 3. So how do we determine what are significant figures in a value? Well, all non-zero digits and 0 between non-zero digits are going to be significant. If you have zeros at the end or to the very right of a number, and there is no decimal place, and there is a decimal place, right? All of those zeros on the end are going to be significant. If I have zeros at the beginning or to the very left of a number in a small number that's less than 1, those zeros are only placeholders. And if I have a really large number that has a bunch of zeros to the left, if there is no decimal place, then those digits are not significant. Let's take a look. So if we have the example 300, right? We can say that if we have a value that's got a bunch of zeros and we want to represent the number of significant digits, let's say our ruler or our measuring object can easily measure up to the tens place, and we want to make sure that the number that we're given shows the correct number of significant figures, we would write that in scientific notation. And that would be 3.0 times 10 to the 2 meters. How do we know that it's times 10 to the 2? If the decimal place, imaginary decimal place is here at the very right of this number, if I move it over to the left 2 spaces, 1, 2, that would give me 3.0 times 10 to the 2. This 0.0 on the end tells me that I have 2 significant figures. What if I have this number 300 and I wanted to represent all of these zeros as significant? I could write a decimal place at the end of the 300, right? Or I could write it in scientific notation and keep both of those zeros on the end. Notice that there's no way for me to indicate that this first zero is significant by adding a decimal place. That would change the whole value. So by writing it in scientific notation, it helps us to preserve the number of significant figures. So when one or more zeros and a large number are significant, place a decimal point after a significant zero at the end of a number. So like we did here, 300, I put the zero after the decimal place afterwards, the decimal point afterwards, and then we have both of these zeros are significant. So zeros at the end of a large standard number are not significant if that number doesn't have a decimal place. So if I have 400,000 grams, none of these zeros are significant. I have only one significant figure. And if I was to write that in scientific notation and I wanted to recognize only the 4 as significant, I can convert that to scientific notation by taking our imaginary decimal place here and counting 1, 2, 3, 4, 5. And being that this number is larger than 1, and we moved our decimal place to the left, I'm going to have 4 times 10 to the positive 5. Because if I multiply 4 times 10 to the positive 5, I'm going to get 400,000. Okay? What if now I want to represent this 850,000 having 2 significant figures? Well, if I put the decimal place here in between the 8 and the 5, what did we do? We moved over 1, 2, 3, 4, 5 spaces, and that would give us 8.5 times 10 to the 4. I'm sorry, times 10 to the 5 meters. Notice that we have 2 significant figures. Zeros at the beginning of a decimal number are not significant. They're just holding a space, right? They're holding a space. If the time is 0.0004 seconds, those zeros are just holding the place to say how very small this number is. And so we have one significant figure. None of these zeros are significant. They are not a part of my measurement. The same for here. There are no zeros at the end of this number, so we can say that there are 2 significant figures in this value. And if I want to change that to scientific notation, notice what I've done here. That if I move my decimal place to the right, because this is a number that's greater than 1, but I'm sorry, that's less than 1, but greater than 0, I'm going to move my decimal place to the right 1, 2, 3, 4, 5, 6 decimal places, and I'm going to write that as a negative value. because this number is less than 1. So I'd have 4.6 times 10 to the minus 6 grams. That represents 2 significant figures. Okay? Let's take a look at a little bit more practice. So a number is a significant figure if it is not a 0. Notice that in these two values, there are no zeros anywhere in this number, and all of the digits that are involved in these measurements are significant. I can count 1, 2, 4.5 grams gives me 2 significant figures. 122.35 meters gives me 1, 2, 3, 4, 5 significant figures. Notice that for these values here, there's a 0 in between non-zero digits. Well, they're sandwiched in between actual numbers, right? Because 0 means nothing. But if the 0 is in between two values that have meaning, then that 0 is significant. So 205 meters gives me 1, 2, 3 significant figures. Whereas 5.008 kilograms gives me 4 significant figures. So it's important to note that, remember, significant figures have to do with measurements. Although you may be asked a question, how many significant figures is in this value? Keep in mind that that value is related to a measurement. Notice that if we have zeros at the end of a decimal number, right, a number that has a decimal place in it, all of those zeros to the right of the non-zero digits are significant. 16.00 grams has 4 significant figures. What does that mean? That means that the balance that we use to take this measurement can read up to the second decimal place. What does it mean when we have here 50 liters? That means that this graduated cylinder can only read up to the ones place. We cannot read to 1 decimal place on that graduated cylinder. Okay? When you're looking at numbers in scientific notation, all of the digits in the coefficient, so the number that comes before the multiplication sign is what we're called the coefficient. So in scientific notation, you have the coefficient times the power of 10. So all of the digits that are written in the coefficient of a number in scientific notation are significant because there's a decimal place in it. We looked at an example already where we had those leading zeros that are significant, but what about trailing zeros, right? Again, they're placeholders. Right? If I have 850,000 meters and I'm measuring that exactly, if there's no 1, there's no 1. It's just a placeholder. I'm trying to get to this really large number and I need those zeros to hold a place for me. But notice there are no decimal places in this value, so only the non-zero digits are significant. The 8 and the 5. That means that my instrument cannot read all of these small values, right? And so any number without a decimal point that has zeros on the end are not significant. Let's do a little bit of practice so that you can be prepared when we come to class, when you come to live lectures. How many significant figures do the following measurements have? Let's count them. Is there a decimal place? Yes, there is. Is there a number sandwiched in between countable numbers? Yes, there are. So how many do we have? We have 6 significant figures. How about in this next number? Remember, yes, there's a decimal place, but these zeros are at the beginning of the number. Do they count as sig figs or do they not? They don't. We only have 2 sig figs. Leading zeros are not significant. What about this value here? 3,400 kilograms. Do we have a decimal place in this value? No, we don't. So we only have those 2 non-zero digits, and those are our 2 significant figures. Our trailing zeros without a decimal place are not significant. What about the last value? 3,400, well, 3,400.0 meters. Notice that we've got a 0 on the end and there's a decimal place. So do we count all of these zeros as significant? Sure we do, because there's a decimal. That means that these 3 zeros are significant and we have 5 significant figures.